So our colloquium speaker today is Terence Tao from UCLA. He's given the second Dvoretzky talk about small and large gaps between primes.
Okay, thank you. So I'd like to talk, as Tammy said, about recent progress in understanding gaps between primes, both small gaps and large gaps. So this is developments that have happened in the last 2 years and actually got a fair amount of attention. You probably heard about some of these already. So, of course, you all know what the prime numbers are, P1, P2, P3. Okay, so these are the prime numbers. So we're interested in the gaps between consecutive prime numbers. So the first gap is 1, and then 2, and 2, and 4, and so forth. And we're interested in how small and how big these gaps can be. Okay? So the question is how small. Okay, now of course you have to formulate this question properly, otherwise it's trivial. For example, how small can the gap between primes can be? It's 1, right? 2 and 3. The more interesting question is how big is the gap between primes eventually? Okay, how small can you make the gap between consecutive primes after some finite point? So what is the lim inf of this gap? Okay. So, so the first gap is 1, but all the other gaps are even because primes are odd after 2. So this is an even number, or it's infinite. But we don't know what this number is. We conjecture it as 2. That is the twin prime conjecture, but we don't know that yet. Okay, but this is the basic question about small gaps. Okay, so if the lim inf is h, this means that you have a gap of size h infinitely often. Okay, so that's a small gap question. And then for large gaps, the natural thing to do so of course the primes get sparser and sparser as you go to infinity, so the gaps should get bigger and bigger. So the largest gap should be infinite. So that's not such an interesting answer. So the more interesting question is if you only look at the primes up to some threshold x, and you ask what is the largest gap up to that x, that should grow in x, but how fast does it grow in x? So how does this largest gap grow as a function of x? Okay, so this is the small gap problem, this is the large gap problem, and there's been progress on both of these problems in the last 2 years. And rather amusingly, the key breakthrough that simplified the work here was for small gaps was also crucial to make progress on large gaps, which is actually rather unintuitive actually, but that's how it works. We'll see why at the end of this talk. Okay, so let me talk about small gaps first. So okay, so we have the prime number theorem, which says that the number of primes less than some threshold x is basically x over log x times a little error. And this already gives you some control on prime gaps. This tells you that inside any large interval, say x2x, there's a prime gap of size at most log x up to an error. Okay, so so this just comes from the original principle. Okay, because the number of primes between x and 2x is about x over log x from the prime number theorem, and so so just from the prime number theorem, two of those primes have to be within log x of each other. Okay, let me give you a second proof of what I just said, which is more roundabout, but there's a reason why I want to say it that way. Okay, so another way to say that, to explain why we have this prime gap is you can prove this. You can prove this probabilistically. Okay, so alternate proof. Okay, so I just pick a number n, pick a natural number n, uniformly at random. From x2x. Okay, so we have interval from x2x, pick a number n at random. The prime number theorem tells you that the probability that this number is going to be prime is about 1 over log x, up to a small error. Okay, so the prime number theorem tells you that it's not very likely that you're going to be prime, but there's about a 1 in log x chance that you are prime. Similarly, if you shift n by 1, and you ask how likely is n plus 1 prime, if you take a random number between x and 2x and you shift by 1, you still pretty much get a random number between x and 2x, and this probably is also about 1 over log x, plus a small error. And same for p n plus 2, and so forth, up to, let's say, p n plus k, where k is just going to be a number just slightly bigger than log x. Okay, so you pick a number at random, you shift it by 1, 2, 3, 4, up to k. All these numbers have about a 1 in log x chance of being prime. So if you pick k just a little bit bigger than log x, you can make these probabilities sum to be bigger than 1. So you can make the sum I equals, say, 0 to k. So eventually, you can make these probabilities sum to be bigger than 1. Okay, for k just a little bit bigger than log x. And then if you have a whole bunch of events whose total probability is bigger than 1, then from the pigeonhole principle, again, somewhere with positive probability, 2 of these events have to occur simultaneously. Okay, so there must be somewhere where n plus I and n plus j are both prime, and that gives you a prime gap of at most j minus i, which is at most log x. Okay? So that was a much longer way to give you the same argument, but I have a reason for doing it. All right. Okay. All right. So this is the trivial bound of log x. It took a long time. So I think that there was first work of Erdős back in like the 40s or something, which managed to reduce the trivial bound of the pigeonhole principle from 1 log x to 1 minus epsilon log x for some fixed epsilon, and then this 1 minus epsilon got lowered to half and like 0.4, 0.3, and so forth. There was a big breakthrough of Goldstein-Prince-Yildirim in about 2004, where they could show that inside this interval x2x, you could actually get a prime gap, which was little of log x. Okay, log x times something that went to 0. So not yet bounded, but growing slower than log x, and this was about 2004. And then the big breakthrough in 2013, in fact I even have the date, it's 21st May 2013. Okay, so what was by Zhang, who showed that in fact you can find a gap in this interval x2x, you can find a gap bounded by some fixed h, which he in fact computed, well, the way he computed it was 70 million for x large enough. Okay, for x sufficiently large. Okay, so he was the first to actually show bounded gaps between primes occur for arbitrarily large primes. And then very, very soon after Zhang wrote his paper, so he wrote this bound is not optimal, but he's not going to try to improve it. But it was very, very tempting to start improving it. I think within weeks of this paper coming out, just over the internet, people were saying, I can move this 70 million down to 60 million, 50 million, and so forth. So eventually we organized what's called a polymath project. It's a collaborative online project whose goal was to make this number reduce as much as possible. And by 27th of July, okay, we managed to get h down to 4,680 by pretty much optimizing every single thing in Zhang's paper. And deploying huge computers and so forth. Okay, so this is, but then there's a second breakthrough by James Maynard. And this date was, where was this? This was October 23rd. So he found a much simpler proof than Zhang's argument. Zhang had, Goldstein, Pinson, and Yodom got very, very close to proving bounded gaps, but they were missing one ingredient, which was they didn't have a good equidistribution estimate for primes in short arithmetic regressions. And Zhang worked very hard and got a non-trivial equidistribution result, which was quite high-tech. It used the machinery of Deline's proof of the Riemann hypothesis over finite fields, for instance. But then Maynard found a way to avoid all that and actually have a much more direct proof, which gave also a significantly shorter, smaller h. And also, not only that, he was able to prove for the first time, not only could you get gaps between consecutive primes, but also gaps between primes that are not quite consecutive. So rather than look at Pn and Pn plus 1, you can look at Pn and say Pn plus 5. And this you can also make bounded by some h, depending on k. In fact, I think k behaves something like k cubed equal to 4k, if you want to be absolutely precise. So not only do you have pairs of nearby primes, you actually have k-tuples of nearby primes as well. And then Maynard joined the polymath project, and then soon afterwards we actually, so this was April 2014. Okay. We got h down to 246, which is still the current world record. Okay, so what we would like is to get h down to 2. That would be the twin-prime conjecture. Unfortunately, we know that these techniques, there's a barrier that prevents us. So these are all based on sieve theoretic methods. And even if even if you assume those optimistic estimates in our method, the best that you can ever make h out of all this is 6. Which we can reach 6 if you assume some sieve theoretic conjecture called the Elliott-Halberstam conjecture, but 6 is the limit of this method, unfortunately. We have to do something else if you ever want to get 2. But okay, so how are these proven? How are these results proven? So in retrospect, the strategy is very simple and very natural. It just took a long time to realize that this was the right thing to do. So I gave you this probabilistic argument for how you would find a gap of size log x. You pick a number at random. You take these different. You take k different shifts of n, and you make this probability bigger than 1, and then that gives you a gap. So the first observation is that you don't have to necessarily take consecutive numbers here. The same argument. I could shift the n by other things. So if I have any k-tuple of distinct integers, h1 to hk, I can take a random number at n, uniformly at random, shift it by n1, n2, n3, and so forth, h1, h2, h3, and as long as I can make this probability bigger than 1, then somewhere there must be a pair n plus hi, n plus hj, whose difference is, which are both prime, and that will give you, as long as these h's are not too far apart from each other, this will give you a small prime gap. Okay, so that's one observation. So what Goldstein, Pinson, Yodom, their method, their key insight, which is obvious in retrospect, is just you make one tiny change to this argument. So you just pick your natural number n non-uniformly at random. Okay. So rather than pick n at random with the uniform distribution, you can pick n at random with some other probability distribution on x to 2x, and that will change all your probabilities. But if you choose a clever distribution in such a way that you can make all these probabilities a lot bigger than they are for the uniform distribution, maybe you need a lot fewer k's in order to make this sum bigger than 1. But the moment you have this sum bigger than 1 for any probability distribution, you are done. Okay, because then there must be some n somewhere in this interval x to 2x for which 2 of these guys are prime. Okay, and so that's basically it. So so another way of saying that is that you need to find a good weight, a good density function, which I call nu. Yeah, so the whole game is to find a good non-negative function on nu, such that if you sum from I equals 1 to k, the weighted probability. So the weighted probability is the sum of all n nu of n restricted to be prime, n plus h to be prime. As long as you can make this bigger than the sum of all nu n. As long as you can make this sum bigger than this sum, so if you divide by this sum, this is the probability according to this non-uniform distribution that n plus hi is prime. As soon as you can find a weight for which you have this inequality, you have found then there must be some pair n plus hi, n plus ha, which are both prime. And if you replace 1 by 2 or 3 or 4, then you don't just get two guys prime here, you can get 3 or 4 guys prime. This is what Maynard did to get multiple clusters of primes. So okay, so the whole game then is to find a nu for which you can prove this sort of inequality. So you need to find a nu. You need to find a probability distribution where each of the n plus h1s, n plus h2, and so forth have a high chance of being prime. And so we have this whole science, whole subfield of number theory called sieve theory, which is devoted to do exactly that. Basically, you want a function which is supported, which is concentrated on those, not on every n, but on those n for which these n plus hi's are either prime or almost prime, only have very few prime factors. You want to somehow sieve out, you want to remove all those n's for which n plus hi is even or divided by 3 or so forth, because those are very unlikely to be prime. So you want to weight this. And so what Goldstein, Pitts, and Yildirim did was that they decided that the best way to make to choose this weight, okay, they wanted all these numbers to be prime, and so what they did was that they multiplied all these numbers together into one big polynomial. Okay, and asking for all these for many of these numbers to be prime is kind of like asking for this polynomial to have not many prime factors to be almost prime. So then they just applied a standard sieve called a Solberg sieve to this quantity. So okay, not terribly important, but just for the sake of illustration. Yeah. So they used a certain function, a certain sieve weight, which looks complicated, but this is a very standard thing. This is called the Solberg sieve. If you want to restrict a polynomial to be almost prime, you look at all the factors of this polynomial. You take some weighted combination of these factors weighted by this Mobius function. This will give you this is a plus minus 1 function. So that's some signed energy, and then you square it to make it unsigned. And then there's some cutoff function and there's some parameter which you have to choose. But you choose a function which is roughly like this. And this is what Goldstein, Pitts, and Yildirim did, and this is what Zhang did. And then Maynard, and this is what the Polymath project did as well, at least initially. And then what Maynard did was he made this really basic observation. So here you're multiplying all these numbers together, and you're testing, you're choosing a sieve based on the divisibility properties of this product. But you don't have to do that. You could instead work separately on each of these factors, look at the factors of each of these terms separately, and that gives you a lot more flexibility. So Maynard realized that there's what we now call a multidimensional Solberg sieve. That there's a better way to sieve these things. Okay, so there's a more complicated sieve that you can use, which is targeted to the prime factorizations or the factorizations of each of the individual numbers n plus h1 up to n plus hk rather than to the product. And there's a more complicated cutoff function that you have to use. Here, this is just a one-dimensional cutoff. Now you have to use a k-dimensional cutoff. But this is much more flexible. These sieves are a special case of this sieve. But Um,
It's too much, then it's okay.
right. So yeah. So this f is just sort of a nice cutoff. It looks something like that. This f it's a function which lives on a simplex. There's a simplex. Sorry, about 1. So there's a simplex which f lives on. It's a nice smooth function on the simplex. If this function only depends on the sum of these inputs, then this sieve collapses to the previous sieve. But this is a more general sieve because you can pick functions which are not functions of just the sum. So the whole art is to pick this function correctly, because if you stick an arbitrary function in here, you can compute both sides of this inequality, and there'll be some, and they turn out to be some quadratic form depending on f. And so this is a quadratic optimization problem. You want to optimize one quadratic expression of f in terms of another, and it turns out that the optimal choice of f is not a function of the sum, but is a tensor product restricted to the simplex. Okay, so this is a genuinely multidimensional function which you can't see from a one-dimensional sieving. You can only see it in the multidimensional sieve, and this is just a little bit more efficient than the previous sieve. And so by choosing a function of this type and doing all the computations, Maynard was able to choose a sieve for which you had this bound. In fact, the multidimensional sieve is in fact more efficient by about a logarithm. And so he was in fact able to make this sum about log k big larger than this sum. And so in fact he proved more than just bounded gaps between primes. So one consequence. The more general theorem of Maynard actually is the following: that given any distinct integers h1 to hk, okay, they have to obey certain admissibility conditions, which I will ignore. Okay, but never mind that, because if I give you k distinct integers h1 to hk, then there exist infinitely many natural numbers n such that n plus h1, n plus h2 so what we would love to show is that every time I give you some numbers n1 to h1 to hk and I shift them, I can make all of them prime. Like n and n plus 2 both prime, or n plus 2 and plus 6 both all 3 prime. That would be great, but we can't do that. But what Maynard could show is that given any k-tuple, if you shift a k-tuple by some n, you can eventually find a k-tuple which contains about log k primes. Okay, that you can find k-tuples that not all k, we can't guarantee all k of them are prime, but we can guarantee quite a lot of them being prime. Okay, and this is what comes up as method. Okay, there's a minus a big O of 1, but okay. All right. In particular, once k is I think like 50, you can get 2 primes, and this is where you get these bounds like 246 coming out. Okay, so that's all I want to say. Okay, so yeah, so actually in the end, it became quite simplified. The final proof you can actually give in a graduate number theory course, in a few weeks. It's not actually as hard as it used to be. Okay. But I'm going to move on now to large gaps between primes. Okay, so remember we have this quantity g of x, which is the largest gap. From 1 to x between primes. And we want to know what we can say about this. So we have this pigeonhole argument from the prime number theorem. So the pigeonhole argument tells you that that there must be a gap which is at least log x, again from the prime number theorem. What about upper bounds? Upper bounds actually are quite terrible, actually. So there's a trivial bound of x. Okay, that's not very interesting. It's actually already pretty hard to get better than x. So the prime number theorem will give you like x over log x or something. But if you assume the Riemann hypothesis, Riemann hypothesis implies, even the Riemann hypothesis, which is quite a strong hypothesis, the best bound we can get, assuming the Riemann hypothesis, is basically a square root of x, is with our Kramer. So there's a huge gap between log x and x to the 1/2. And Kramer actually conjectured, that actually the correct size of the gaps between primes should be about log squared x. His reasoning was that if you pretend that the primes behave like a random set of density 1 and log x, then the gaps between primes should have, on average, log x size. That's the prime number theorem. And the gap should follow an approximate exponential distribution. And then if you just follow the calculations, you predict a log squared. But you can see even with the Riemann hypothesis, we're well short of this goal. Unconditionally, the best bound on g of x currently is x to the 0.525. These are Baker-Harman pins. So, better than x, but a bit short of root x and well short of log squared x. Okay, so that's the state of the art for upper bounds for g of x. Okay, so now I want to talk about lower bounds for g of x. So, how can we produce big gaps between primes? Okay, so we have this pigeonhole argument, which produces gaps of size log x. Another simple argument, which many people even learn in high school, it's a very simple way to generate large gaps between primes. See, large gaps between primes is the same thing as having a big consecutive string of composite numbers. Okay, so if you can find a big string of numbers, consecutive or composite, that guarantees you a big gap between primes. Okay, and so here is a way to generate a big, nice long string of composite numbers. Right? N factorial plus 2, n factorial plus 3, and so forth up to n factorial plus n, they're all composite. And the reason is that the reason for this is that if you look at this interval from 2 to n, every single number in this interval is divisible by some prime less than n. And so these are all composite. And so if you plug this into Stirling's formula, what this gives you with a little short Stirling's formula computation is that the gap between primes up to size x is at least log x over log x. So that's not so great because that's even worse than the trivial bound. But you can do better. You don't have to use n factorial. There's a slightly more efficient version of the factorial called the primorial. The primorial of a number is defined to be the product of all the primes less than n, not all the natural numbers less than n, just the primes less than n. And that's good enough. Okay, so you can take the primorial, which is a bit smaller than the factorial, and these numbers are still all composite because, again, every number in this interval is divisible by some prime less than p. Okay, and if you use now not Stirling's formula but the prime number theorem, and you work it out, what you find is you get a bound of log x, which now exactly matches the trivial bound rather than being worse than it. Okay, so all right, so what? Okay, so we haven't actually improved the trivial bound yet, but you just need to be more efficient with this covering. So more generally, if you can cover an interval, okay, so I started from 2. I'm going to shift it down to 1. Doesn't really matter. If you can cover an interval from 1 to y using one residue class, mod p, for all p less than x, then this same argument, together with the Chinese remainder theorem, tells you that you can make this gap bigger than y for x about the size of e to the x, e to the little x. Okay, that if you can find a residue class mod 2, a residue class mod 3, residue class all the way up to mod x, with all the primes up to x, and if you can cover this interval completely, then by the Chinese remainder theorem, there must be some way to shift this interval so that every number in this shifted interval is divisible by one of the primes up to x. And the biggest shift you need is actually the primorial of x. And so you get a bound like this. And so if you can be more efficient in covering, so here what we're doing is that we're using the Safra Eratosthenes. This particular interval here is covered by 0 mod 2, 0 mod 3, up to 0 mod, well, all the primes up to n cover this interval. And if there's some way to cover this interval more efficiently, using maybe a larger interval more efficiently by maybe shifting these residue classes, then you could do a more efficient shift. So people started doing this. So I think the first results that started improving on this trivial lower bound of log x were by Cynthius, and then Erdős, and then Rankin. And so there were slight improvements to this bound, and then so I think in around 1937 or something. Okay, so for a long time, the best bound known was log x, log x, log x over log x squared. Okay, so there was a series of improvements. They were adding more and more weird logarithmic factors. There were some previous bounds which also looked like this, but slightly worse. And so, all right, so I mean, they were better than the trivial bound, but still well short of the conjectured bound of Kramer, which is log squared x, and this is significantly weaker. Okay, so there was always progress, but then it stopped at this strange bound for like, so then for the next like 70 years, what happened was that this C was initially like 1/3, and then it got, the only progress in the next 60 years was to improve this C, from like 1/3 to, I think eventually 1.2 or something. And in fact, you know, it was so stuck that at one point, Paul Erdős actually offered a big prize, I think $10,000 to anyone who could actually move beyond this type of bound and replace this C by something which goes to infinity. Actually, strangely enough, it was actually the biggest prize he'd ever offered, actually, for such a weird problem. Okay, so we were stuck here for a long time.
If you work on the problem for 50 years, I wouldn't be
I guess so, yeah. I mean, he definitely worked on this for quite a while. He had many of the previous results before Rankin. Yeah, so eventually, Kevin Ford, Ben Green, Sergei Konyagin, and myself. Yeah, so after 70 years, we were able to, so this was for some C, okay. And then we were able to show that you can take C arbitrarily large. Okay, of course, this is for x sufficiently larger. Okay. You can replace C by something like grows to infinity, although we didn't specify exactly how fast it could grow. So it was some number of logs, but we didn't actually specify exactly what it was. Although the weird coincidence, you know, so 70 years, or in fact even 80 years of no progress, but then the very next day, James Maynard gave an alternate proof. Okay. Same theorem. And then we joined forces. Okay, and then this year. Okay, so all. Yeah, sorry, myself. And then all of us. Actually, I didn't put the date down, but it was 2000. I think January this year. No, actually, no, it was maybe just actually December of last year. Okay. So actually, we finally figured out exactly what we can squeeze out of all our methods, and it turns out that if you optimize everything. You get, okay, basically you get to remove a square. You get to improve one log. And then weirdly, then we got stuck here. it seems like there was no further thing. To improve this would actually be quite a challenge. In fact, I ended up offering the same cash prize that Erdős did, $10,000 to anyone who can improve this, because this is the limit of our method. Okay, so where do all these weird bounds come from, and how do you prove these things? So all these arguments follow the same strategy, which is you basically have, as I said, you have this big interval from 1 to y, and you want to cover this interval as efficiently as you can using using one residue class mod p for each p, and the bigger you can make y as a function of x, the bigger that the more you can do here. So what Rankin did was Rankin could take x y just a little bit bigger than x. Yeah. So the y that he could get was of this shape, and we were eventually able to get rid of one of these log x's. Okay, so the way I like to think of this is like you're shooting ducks. Like in this, there used to be these fairs where you would go and you try to shoot these toy ducks for prizes, right? And so you have these Y ducks in a row, and you have a mod 2 gun that you can shoot either 1 mod 2 or 0 mod 2. You can knock down all the even ducks or the odd ducks, and then you have the mod 3 gun. You can knock down one of the residue class mod 3, and then mod 4, mod 5, mod 7, and so forth. You get to shoot each gun exactly once, and you have to knock down all your ducks. And the question is how to do that as efficiently as you can. Okay, so there's the okay. So the first observation is that rather than have to shoot down all the ducks, it's enough to shoot down most of the ducks if you save some of your ammunition. So it's enough to cover all but about x over 2 log x of 1 to y using a residue class mod p for all p not up to x but up to just x over 2. Okay, because suppose you shoot all your ducks using all your primes up to x over 2, and suppose you manage to knock down most of the ducks, but x over 2 log x ducks survive, but you still have all the primes between x over 2 and x are still available for you to choose. And the number of such primes you have is about x over 2 log x. So basically, for each remaining prime, you just target one duck, right, and you just choose a progression to knock off one of the remaining survivors, and so then you can cover everybody. Okay, so just by making this tiny change of reducing x to x over 2, it's okay to have some ducks left over. You just need to cover most of the ducks. Okay, so that's the first observation. Now, okay, so we have the Safra Eratosthenes. Okay, so that worked reasonably well. So you can start there. So you can try using 0 mod p for all p up to x over 2. In fact, let me just use the p's up to x over 4. So you can just try shooting 0, 0, 0, 0 all the time. And if you do this, you will knock down a lot of ducks. The only people that will survive, the only ducks that will survive this process from the Safra Eratosthenes, so the only survivors are the primes bigger than x over 4 and between x over 4 and y. Okay, these are the only numbers. So any number less than y is either prime or it's divisible by at least 2 primes, and one of the primes is going to be less than x over 4 because y is only going to be a little bit bigger than x. It's like x log x times a little bit. Okay, so if you just use 0 mod p, this already gets rid of a lot of your ducks, but you keep the primes. Okay, now that by itself is not so great, but you can observe that you can be more efficient here. You don't need to knock out all the primes. You can just knock out all large primes and also all small primes. Maybe a 4 here. Okay. If you remove 0 mod p for all small primes and all large primes, But you leave out intermediate primes between this number and some threshold z. Then you still have then this still pretty much does the same job. That the only numbers that survive are primes, big primes, and also what I call smooth numbers. Okay, so z smooth numbers actually, numbers with all prime factors less than z. Okay, because if you remove all multiples of p in this range, the only numbers that can survive are numbers that have one big prime factor, so the big primes, or numbers that only have lots of small prime factors. And if you choose z correctly, you can make this set small. You can make it small enough to just fall into this your acceptable error term. So you can just pick z to optimize this. And so there's a formula for how many z smooth numbers there are up to a certain point, and it's sort of complicated. And it turns out that the optimum z is x to the log x over a constant times log x. Okay, so it turns out if you just plug in the formulas for smooth numbers that the correct z to choose is this, and this is the main reason why we have all these weird factors coming out here. So if you do that, then you can get rid of these numbers. These are already negligible. Then you have so now you have two remaining sort of rounds of ammunition you can play with. There's these medium primes. And then there's still the very large primes that you can play with. And so what people do, so for the medium primes, actually the most natural thing to do here is to shoot randomly. Okay. Okay. So here there's no point doing any more Safra autosthenes because the Safra's already done his job. So you just sort of shoot randomly, and this will cut down some of your survivors. So rather than look at all the primes, you end up with some sort of random subset of the primes. So this was already understood by Rankin. In fact, that was basically Rankin's big contribution to the whole subject. And if you just do that, actually, that already gets you as far as Rankin's bound. And then the only remaining game is what to do with these last few primes here. So so what Rankin did was that he basically just used this previous trick. That for each of these primes, he just covered one survivor. He used each of these primes to shoot one duck. Okay, and because that was the best he could do. And then there's some later work by Meyer and Pomerantz, and basically their idea was to use these primes to shoot two ducks each, rather than one, and so they can improve this constant a little bit. So basically, what you need to do to make more efficient use of this last set of residue classes. See, each residue class is giving you so for each p, you've got a residue class. And you get to pick this A. And basically, you want to pick residue classes that are efficient, that cover a lot of ducks. Okay? So you want to find progressions which capture a lot of primes. So the reason why Ben and I got involved in this is that Kevin Ford and Sergei Konyagin were working on this problem, and they suddenly realized that they needed people who knew how to find progressions in primes. And Ben and I actually had a theorem about that. So So Ben and I had about 10 years ago had a theorem that showed that you could construct arithmetic progressions, a plus r, a plus 2 bar, and so forth. You could find arithmetic progressions of any length you wished, which captured a lot of primes. In fact, in which these numbers are all prime. And in fact, you can modify that argument using later work of Ben and myself, and also Tamar here. You can find actually not just progressions of primes for which everybody's prime, but you can actually find progressions of primes where the spacing itself is prime. Actually, you have to shift the prime by one. Well, that's not quite true because this particular progression, like every other number, is even. But you have to modify p by k factorial. But but roughly speaking, you can modify this, some old work of Ben and myself and Tamar, to find lots of progressions whose spacing is basically a prime and where every entry is prime. And so what that does is that it allows you to find lots and lots of primes here, which don't just shoot one duck each, but they shoot many ducks each. And that was what we did to make this constant arbitrarily large. But then James Maynard observed the next day, that independently, actually, I mean, there's no, yeah, but I mean, you don't need every single element in this progression to be prime. You just need many elements in the progression to be prime, and that would already do the job of being more efficient than all previous algorithms. And so this problem of producing progressions where many of the elements in the progression are prime is extremely similar to the problem that came up in prime gaps. So Maynard had already showed that given any k-tuple, you could find many shifts of that k-tuple for which many of these guys are prime. So in fact, you can find you can find at least log k primes in this k-tuple. And this is almost the same problem. It's just yeah. I mean, it's almost exactly the same problem. That you have a plus p, a plus 2p, a plus up to a plus kp, and you just want to find lots of a's for which this for which many of these guys are prime. And so it turns out that basically a routine modification of the argument of Maynard that gives you this also gives you, if you have a progressional length k here, you can make about log k of these guys prime. And this ultimately is what gives you a very similar result. If you push all the arguments through, so if you just plug this in and do all the calculations, you don't quite get this final bound. You miss this extra log factor. The reason is that there's so what happens is that using this sort of mechanism, each of these primes gets to shoot out log k ducks, and so you would think therefore that because you're now shooting log k as many ducks with every shot, the total number of numbers you can cover should be multiplied by log k. But that's not quite true because there's overlap. These primes aren't. I mean, they're not coordinated with each other. So each of these primes is eliminating some subset of primes, but they're all random. Okay, and so there's a lot of overlap. There's a lot of waste. You're shooting the same duck over and over again, and so you don't actually gain the full log k. You gain log k over log k if you shoot randomly. And so you lose this final log factor. And so the final thing that we did was that we realized that this problem was actually an instance of a very well-studied graph theory problem, or actually a hypergraph problem. So the basic problem we had here was actually an instance of what's called a hypergraph covering problem. That you have some set of vertices, n vertices, and you have various families of subsets, of say k element subsets. Okay, so each of these are sort of what you can, what one of these bullets can, one of these guns can shoot. How many ducks? So this is a whole set of ducks, and you want to cover your whole set n, or maybe most of your vertex set, using as few of these. So you're given some family of k element subsets. So that's what a hypergraph is, a family of subsets. And you want to cover most of your vertices by as few of these as few of these k element subsets as possible. So the theoretical limit of the least number that you could possibly use is by n over k. You wanted to cover all of these guys. But if you try a random, if you just choose these k elements as randomly, you will find that you will lose effect of log k just from random overlap. But there's a nice theorem of Pippinger and Spencer using what is called the semi-random method of Rodo, that shows that, that actually, if these k-lemma subsets are sufficiently so uniformly distributed in your hypergraph, then actually you can get rid of this log k, just lose a constant. That the idea is actually you do what's called the rotor nibble. So rather than just pick all these k's randomly, so rather than just sort of shoot randomly, you shoot randomly for a short period of time. So you remove a small number of these guys, and then you recalibrate, because then once you get rid of some of these guys, you remove all the k-element subsets in your hypergraph which touch the elements that you already selected. So you only keep those k-element subsets that are disjoint, so that they would remove that they're going to not overlap the previous guys. And then you shoot randomly for a little bit more. You take another nibble. You randomly select a few more, and then you cut those out, and then you readjust, and so forth. And so this was done by Pipitcher and Spencer, at least in what's called the uniform case, where all these sets have the same number of elements. And so what we had to do is that we had to generalize the Pipitcher-Spencer theorem to a non-uniform setting. In our setting, each residue class actually contains a variable amount of primes in them. So we had a non-uniform hypergraph. But it turns out that if you do things properly, there's also a non-uniform version of this hypergraph covering lemma, and using that we could finally get rid of, lose this inefficiency and get back this bound here. So that is our bound. It is this is the limit of what we can do now, for two reasons. One is that these methods of Maynard, in any k-tuple, we can only produce log k primes in any k-tuple. And that is a hard limit of this sieve theoretic method. We know that no sieve of the type that Maynard considers can do any better than log k. So you would need a breakthrough in sieve theory if you wanted to improve that log k. The other thing is that this whole approach of finding large Castrian primes by finding chains of composite numbers, each of which is divisible by a small prime, it's inherently limiting. You see, this procedure can only give you chains of composite numbers where every number in this chain is divisible by a very small prime. But we expect for the largest Castrian primes that they should come from chains of composite numbers where the composite numbers are composite not because of small primes, but because of big primes. And but we have no idea how to produce composite numbers with big prime factors that are next to each other. We can only do it with small prime factors using the Chinese remainder theorem, and because that's the only tool we have. But if you don't, absent that, if you don't find a way to produce composite numbers with large prime factors, the best you can ever get from this sort of strategy, so the ultimate limit of this sort of method is about log x squared. So even if you solve this log k problem, the limits of Maynard sieve, this is the best you can ever get by this general method, and something much more difficult will have to be done if you want to get any closer to Cramer's conjecture than that. But we can at least move this 70-year-old bound by a little bit anyway. Okay, so thank you very much. Yeah, so this, I believe so. The conjecture has had to be fixed once already. So Cramer originally conjectured actually a stronger conjecture that in fact the largest gap was actually asymptotic to log x. Because that is what happens if you have a purely random set of numbers of density log x. But this is no longer believed to be the case. There are portions of the integers where the primes are a little bit sparser than average. That there's a little bit of non-randomness in the primes, non-uniformity. And Andrew Granville, about 20 years ago, sort of focused his attention on a certain special subset of the natural numbers, and using some probabilistic heuristics, he actually conjectured that you should be able to gain a little bit. The bound 1 here should actually be increased to 2 to the e minus gamma, which is about 1.2. That Kramer's conjecture was off by about 10-20%. This may not be the best bound. There may be an even sparser set there may be another region of space where the primes are even sparser and you get slightly larger gaps. But it seems hard to do much better than Granville's construction. So I think it's still likely that the correct bound is comparable to log x squared x. Yes?
What's when you're shooting ducks in the graph covering case,
Mhm.
hypergraph covering, what's the advantage of shooting them randomly over just shooting one set and then saying, or taking all the sets that don't intersect that next time?
It's because it's a bit technical. It's because it's hard to understand the remaining. There's a certain inductive hypothesis that you need to keep the remaining sets sort of uniformly distributed over your vertex space, and if you remove things deterministically, it's very hard to control the remaining sets. But if you remove things randomly, it's easier to control the surviving sets. So it shows up in when you have to verify this inductive hypothesis. Yeah. I mean, morally it should make a difference, but from the point of view actually proving that your analysis works, it's more convenient to work randomly. Yes.
Here you discuss the maximum gap between primes
Yes.
up to x. Can
Yes.
you say something? Can you estimate the average gap up to x?
Right, yeah, so that's an interesting point. So of course, the first moment, the actual average gap is log x from the prime number theorem, the first moment. We don't know, if you just compute the average, I mean, this over, this is log x. We would love to, so we believe that these gaps are distributed according to an exponential distribution. So the proportion of gaps which are bigger than, say, a log x, okay, this should be by e to the minus a times the number of primes up to x. Okay, this is the conjectured distribution, exponential distribution. But we can't prove this at all. People have studied some related problems. You can look at limit points. You can look at normalized. You can look at normalized prime gaps. So these are normalized to be of size 1, and you can look at the limit points of this set. Okay, so what are the numbers such that Pn plus 1 over Pn over log Pn converges to that number? Okay, so for example, this contains 0, and it contains, because of the small gaps results, it contains infinity because of the large gaps results. And it should contain every number in between. So we don't know that yet. What we do know is that this set has positive density. In fact, it's synthetic. And it contains 0, it contains some neighborhood of the origin. So it contains, it's sort of large, but we can't even prove that it's everything, which is definitely what it should be. So there's some limited information that we can prove. By the way, these results, they were proven using also a variant of this Maynard theorem. About that you can find k-tuples with log k primes in them. Yeah. Yes, Gil.
If you look instead of the number one where values of integral polynomial, like n squared plus 7, something more complicated,
Yeah.
can you have long?
Well, we can't even find one prime.
No, you want a long, many values, consecutive values of the polynomial which are composite. Can you do something similar again?
Oh, I see. Okay. Yeah, there are results. Yeah, okay. Yeah, producing large gaps between primes would be very easy. Small gaps would be, so we don't even know that there's infinitely many primes from n squared plus 1.
But large composites intervals.
Yeah,
can do the same thing.
that's quite likely that some variant of this method should work, because it's all based on small primes, and we understand how polynomials behave relative to small primes. It's again just covering my residue classes, so that should be fine. Yeah.
Okay, so let's thank Terry again for 2 great.